Allora, buongiorno a tutti, benvenuti a questa presentazione 10. La faremo in inglese perché il corso è un corso completamente offerto in inglese, così vi dà anche un'idea di come sono le lezioni in inglese al Politecnico. So, we will start with a first, let's say, sort of lesson related to a topic that is, let's say, one of the topics that we teach in the C program. It will be how to send a picture from Mars. It will be given by my colleague, Professor Guido Montorsi, that is an expert in this field and is working on this area at, let's say, at research level. So, Guido, thank you.
Okay, can you hear me? Good morning, everyone. My name is Guido Montorsi, and today I am trying to explain you in like just 20 minutes how to send a photo from Mars. That is quite apparently a challenging task. As we will see, is not a very big and complex task. Let's start with the problem data, what we want to do. Let's suppose that we want to send a picture, a JPEG photo, and the size of this picture is like 1.5 megabytes. That corresponds to like 12 megabits. And so the problem that seems very complex is that the distance from Earth to Mars is quite large. Here you see in this graph, that looks like sinusoidal distance from Earth to Mars that range from 0.5 to 2.6 astronomical units. That corresponds to a distance between 75 and 400 million kilometers. Right now, I checked it like last week, the distance from Earth to Mars is 264 million kilometers. And one thing that we have to fix is the frequency that we want to use, the frequency for carrying the signal. Usually for deep space communication, we use the X band that range from 8 to 12 gigahertz. And in my example, I will use a frequency of 8 gigahertz. So let's start. Okay, with a very important equation that is the one that you find here on the top right, that is the phase transmission equation. Basically, it tells you what is the received power if you have a given transmitted power, PT, at a given distance, that is D. And then there are two additional terms that depends on the diameter of the antenna that you are going to use, that is GTX and GRX. And we start with commenting this first part. So the big and the small factor is this 1 over D squared, that is the distance from Earth to Mars, that is very large. So if you compute this number, 1 over D to the square, you get this very, very tiny number, 10 to the minus 23, that is 0 followed by 23 0. So it's a very, very small factor. And of course, in order to increase the received power, what you can do is you cannot change the distance, so you can only increase the transmitted power. Now we are considering the so-called downlink, what goes from Mars down to Earth. So actually the transmitter here in my example is located on the rover, for example. This rover has not many available power, of course, because you receive the power from basically solar cell. So the amount of power available to the transmitter is quite small. Here in my example, I'm assuming just 5 watts. If I'm considering the uplink going from Earth to the rover, as you can see, we may assume a much larger transmitted power. So now this is the first part of the picture. We have 5 watts, and this factor here is very, very small. Now what we can do, instead of just speaking loudly, is to increase the antenna gain. That means basically to open the ears. And so basically we can act on these 2 factors that are related to the diameter of the antenna, the transmitter, and diameter of the antenna, the receiver. So this gain basically can be obtained by just dividing the true diameter D divided by the length of the carrier, the wavelength. In this case, you cannot see it here, we are using 8 gigahertz, so the length of the wavelength is 3.75 centimeters. So the ratio D over L raised to the square give you like a factor of 3 million for the gain at the receiver, because you are using a very large antenna. You see it there, like 70 meters of diameter. On the other side, of course, again, at the transmitter, you don't have a big antenna. So the diameter of this antenna is much smaller. Here, I'm assuming 70 centimeters. And as a consequence, the gain here is much lower, only about 300. So we have to multiply all these factors together. And here you see the multiplication, the transmitter power, the free space loss, the gain of the transmitter antenna, the gain of the receiver antenna. And on top of it, I added this 0.35 that is related here to the so-called pointing loss. The antenna that you are using at the transmitter and at the receiver, they are highly directive. And so you need to point one antenna to the other one. If you make mistake in this pointing, and this is quite normal for very highly directive antenna, then you have so I have to start from scratch. Okay, anyway, maybe because I'm touching the button. Okay. Okay, so the nice thing and the interesting thing is that you can do more than that, is to use a channel code. And here, keeping my analogy with the talking, is to speak properly. You need to use some special kind of message. Actually, you can use what is called a channel code that inserts redundancy in your transmitted bit in such a way that at the receiver, you have a decoder that can correct those errors. So basically, the situation is that you receive your signal with error with some background noise, and then your channel decoder is capable of correcting those errors. And so you get your original transmitted signal. Now, the important parameter for this is the so-called code rate. That is the ratio between the throughput, that is how many bits per second you are sending, and the actually throughput of the transmitted, the number of bits per second after coding. This is called the code rate, and is a factor smaller than 1. So I give you some example of a code rate just to give you an idea on how they work. This is the very simple example. This is not what we are going to use, but it's just to have understand a little bit what is happening. Suppose we want to send either 0 or 1, and instead of just sending 0 or 1, we send 3 0 or 3 1. So basically, we add a so-called 2 redundancy bit, the red one, so that now when we transmit 0, we actually transmit 3 0, and when we transmit 1, we transmit 3 1. So of course, the rate of the code is rate 1/3, 1 input bit, 3 output bits. And at the receiver, what you can do, you count, of course, your channel will introduce some error. So for example, if you transmit 0 0 0 and your channel turn one of those 0 into 1, your receiver is just deciding by majority. So if it counts the number of 0 and the number of 1, if you have more 0, then you detect a 0. And actually, you corrected one error. So of course, this is just a very simple example. We can do much better. And here I give you, I won't go too much into the detail because we don't have much time, but just to give you a hint of what is happening, you can do much better. So for example, I can build a code with 4 input bits, and I add to those 4 input bits 3 additional redundancy bits. You see here the code book. We have 4 bits, so that is 16 possible configuration of your information bit, the green one. And on top of it, we add 3 red bits that are redundancy bits. And we build this that we call the code book, the set of possible messages. Now, the way we build this code book is a particular construction that I cannot comment, and the receiver is more complex. But the fact is that with this code book, you can still correct one error, exactly like the code before. But now the rate, instead of being 1/3, like here, now it is 4/7. And actually, there is a whole theory that is called coding theory that allow you to build those set of messages that are correcting errors, and also a theory that tells you what are the limits, that is information theory. Basically, the idea is that if you increase the code size, that is the length of your code book is large, and also if you decrease the code rate, you can improve the error correction capability. And actually, information theory tells you how good you can do in constructing this code. And it establishes a limit, this very important limit. This tells you that if you can send for each information bit an energy, collect from the space an energy EB that is larger than a fraction of the background noise, that is M0, then you can build a code that corrects all the errors. So you can send that bit reliably, we say this. So we send reliably, it means we send it and we receive it with no errors. So this is an absolute limit. You can reach this absolute limit when your code rate becomes very low, going to 0, or when the block size becomes very large. So you need to construct very long code. This is a code of length 7, and of course it's very far from this behavior. The fact is now we are capable of building this type of codes. And for example, what we use in deep space communications, that are communication for the deep space, we design the code that have a rate 1/6. This, the nickname of this code are turbo codes for some reason. These are, have been invented like 20 or 30 years ago now. And now the information packet, that is the block size, instead of being 1 or 4, is like almost 10,000 bits. So very large packet. When you increase the packet size, you can correct more error. And with that type of code, the limit, instead of being the absolute limit, because we are using not a very low rate, and also because the code is not ideal, then my limit would be EB greater or equal than 0.95, the level of noise. So that is what we can do, the best that we can do using coding. And now we need to understand how we collect that amount of energy, EB, for each transmitted information. So now we have this limit, energy per bit, and what is the energy that we collect for each bit? We have just to take the power received, PR, that we already computed, and divide it by the throughput, our modern throughput, how many bits per second we want to send. Of course, if I want to increase EB and I have fixed PR, that is 15 femtowatt, I need to reduce the throughput. And this basically, if you just reorder this inequality, you get that the throughput, S, the number of bits per second, has to be smaller or equal than the received power divided by 0.7, the level of noise. And you can plug these numbers that I have already computed. This at the numerator, you see the received power, 10 to the minus 15 femtowatt. At the denominator, you see the level of the noise, 3.5 times 10 to the minus 22. You see these are really tiny number, but at the denominator, this number is much smaller than what you have at the numerator. So actually, this limit is not so low. This is like 61 megabits per second. So if you use proper coding, you can build a modem from Mars to Earth of 60 megabits per second. That is large. This is basically what you are connected with the password, okay? Or yeah, but you can do it. Actually, you know that we can talk and communicate with some spaceship much farther than Mars. Okay, so this is not a really challenging task. So that is basically the conclusion of my talk. If you want to transmit a photo from Mars, you need to speak loudly. So increase the transmit power if you can. You can keep your ears wide open, increasing the transmitting antenna and receiving antenna. You should reduce the background noise. And this is something that sometimes you cannot do. And then this is the interesting part, you can speak properly. You can find the correct way of talking so that the message of the receiver can be comprehended. And finally, you have to speak slowly. You have to slow down your pace so that, of course, the user can collect enough energy for each transmitted bit. And so going back to our problem, since we have 12 megabits and we can transmit at 61 megabits, the computation is just, you need 0.2 seconds to send this photo. It's quite fast. So yeah, that is the conclusion because we only had like 20 minutes. I just have a warning. I skipped many details and these results are very optimistic. So if you want to know more detail, please feel free to ask some questions. And for the moment, that's it.
All right. So the first way to correct the bit sent before coding, was it like where you repeat the bits? So instead of sending just 10, you'd send 000 or 111. That one is it based on luck? Like, how can you be sure that not the majority of them will flip?
No, of course, you are not sure.
Oh, okay.
That particular code is able to correct one error. Of course, if you have two errors, you have an error. Overall, your decoder will not be capable of correcting. So each particular code have a so-called correction capability. Okay, that is the maximum amount of error per packet that can correct. That particular very simple code, the two of one actually, both of them, they have a maximum correction capability of one, sorry. So they can correct an error, they cannot correct two errors, okay? So of course, this depends on the rate of the code, the size of the code. That was very simple code. There are some error correcting code that correct 2 errors, 3 errors, 4 errors, so on. It depends on what you're doing. But the nice thing is the theory tells you that if the code size becomes infinity, basically you can correct most of the error.
Oh.
But
All
this
right.
is, of course, not in my example.
All right, thank you.
My question is that how do you receive signals from other extraterrestrial objects? For example, in this case, we had a transmitter on Mars, which functioned on a certain band
Yes.
from 8 to 12 gigahertz. But what if we want to receive signal from another object which transmits signals on a different band and we don't know the band?
If you don't know, okay, first of all, in my presentation, I totally skipped the problem of bandwidth allocation. That, of course, allows you to put together multiple transmission using different carriers. The bandwidth of the signal that you're using is very small because you're not sending large data rate. Now, if your question is, how do you get a signal for which you don't know the carrier frequency? The only way is to sweep your spectrum and find some energy somewhere. But then you have to find out how to decode it, of course. This is another story. This is like sneaking, and it's a very interesting topic, but of course, this is not what, of course, here I'm assuming that the receiver knows the carrier frequency. Otherwise, you have to find out some power somewhere. Then once you find the power, you need to also decode it. And this is not simple. If you don't know the code, there is no way. This is one type of cryptographic actually using very complex code so that the user that does not know the decoding algorithm is not capable of decoding your message.
Trying to move to the next step, otherwise
Yes. Sorry.
we don't have time to present also something more related to EC. Thank you, Guido. Interesting presentation. Thank you also for the question. So now we will move to a second part that is more related to EC. So now I want to talk about something more specific to EC, to give you some more information about the study plan, about other information. And as I don't want to bother you and be tedious, I will use an object that is in your pocket, the smartphone. So I will try to do a sort of anatomy of the smartphone to introduce the content that we teach in electronic and communication engineering. So what if you would open your smartphone and sort of destroy in pieces? You will find circuit boards, microprocessor like CPU, GPU, graphical processor unit, memory, battery, display, camera, modems that also Guido cited that are modulator, demodulator, so transmitter and receiver in the end, antennas, we see many antennas, and a lot of sensors, accelerometer, gyroscope, fingerprint, barometer, thermometer, that allow you to use the phone in many different ways with many different applications. So now I will try to group this component in areas. For example, let's start with the electronic circuits and devices. You have circuit boards like this one, flexible circuit boards. There are chips for microprocessor, CPU, GPU. There are memory that are other type of chips, like this black square here, sensor that is even difficult to find. And I can show you that all these components are part of the knowledge base of these courses that we have in the study program, the study plan of EC, because we have a course in circuit theory and application, we have a course in electronic devices, a course in electronic circuits, applied electronics, electronic measurements, where you measure the property of these devices, and digital system electronics, where you put everything together and you build, let's say, the electronic system. And then let's look at another part, that is communication devices. Modems, modulator, demodulators, antenna. There are plenty of antenna, Wi-Fi, 5G, 4G, Bluetooth, NFC. So there are probably even more than 5, 6, 10 antennas in a single smartphone. There are some of them listed here, but you cannot easily find them. Obviously, it's not the antenna that you could see outside in the first cellular phone, not even smartphones. And again, in the EC program, we have electromagnetic waves and antenna. That is easy to understand what we teach in there. We have signaling system and digital transmission that are, for example, basic foundation courses in communication, in digital transmission, where you learn, let's say, the basic of what Guido introduced, how to transmit bits in a channel affected by noise. You need to know signals, you need to know system, and build a digital transmission. We have communication network course, where you put together digital transmission, you build a network, you connect nodes, you need to understand how protocol works. And then we have labs, where these things are, let's say, learned also by doing. And we see that this is a peculiarity of EC that we use wherever is possible. Do we have forgotten something inside the phone, say, just as a building blocks? There are electronics, there are communication components, and then the software. We forgot the software that is fundamental. Otherwise, this is just a piece of, say, metal that it doesn't, let's say, it will not be so useful. If you don't have an operating system, iOS, Android, or whatever it is, and apps, application in general, you cannot use your phone. And we have computer science course, basic course, and advanced one in the third year, algorithm program. So let's put all these courses together. I colored them: red area, electronics; green, communication; blue is the software. And then we need to add foundation courses, mainly in the first year. We see some of them are also in the second year: math, physics, chemistry, that you need to learn to move them to the other area. So putting together all these, we have the study plan. So this is what we teach in the 3 years. If you want more detail, it's better that maybe you stop by our booth that is just behind that door. I colored again. You see the orange, yellow are mostly in the first year, some of them in the second. But we also have one characterizing course, and we select the communication network that start to give you some insight in the communication. That is one of the 2 areas of EC in the first year. And then second and third year, you see red and green becomes dominant because we teach you communication and engineering. There are 2 core areas for EC. That is this interdisciplinary program that I'm describing. This is another view of the EC recipe. You see in the plot, in the chart, that there is, apart from 1/3 of foundation courses, but this is more or less the same for all engineering. The first year is common year. We have 1/4 of electronic and, let's say, 1/4 of communication. 1/4 because the gray area that are other courses, that are free courses, you can select them in order to have 1/4 of communication. Otherwise, you can select other courses that could be in other area because these are completely free. There is a catalog of courses. You can also bend towards soft skill, management, even economics. But we suggest you to keep them in the let's say, technical area, and especially in communication, so that you really complete 1/4 and 1/4. And then the remaining is software that is sort of needed together with the foundation courses to learn. So the Bachelor in ECE is an innovative program that we started in 2015, completely taught in English. And you can see in this table that the reason why we decided to teach in English, because we attracted a lot of foreign students. There is a class of international students that is a good thing, also probably if you are Italian, because you blend with them. We started with percentages that are 30, 40, but now we are constantly above 50, above even 60%. In the last year, we had a big jump to 70, even 80%. Our Bachelor program is offered here in Torino, and our group of teachers in electronic communication is very well, has a very high reputation. Just a few days ago, PoliTo released this press release because this Quacquarelli group that ranked the university shown that PoliTo in the area of electrical and electronic engineering is ranked 38 out of 500, more than 500. So we are in the top 10% in this subject area. It is very, very high. And also, if you check Alma Laurea, that is a website where they, let's say, collect information taken directly from students. They ask students at the end of the program. We have 100% student appreciation, as you can see from these plots. So ECE is a program in the ICT area, Information Communication Technology. It's an interdisciplinary program. The two first letters in the acronym are electronic and communication. As you saw, it's a blend of these two areas. But what is ICT? ICT covers all the techniques that are needed to store, retrieve, manipulate, transmit, and receive information in digital form. Okay? And ICT is pervasive. The two main examples are the smartphone that I used in the previous example, internet in general. So everything that is related to this is ICT at large, let's say. Here I listed some applications that are in the area of ICT, and it's something that you, let me say, start learning, because in the end, a bachelor program cannot give you the full and complete, let's say, coverage of all these areas. Typically, you complete them in a master. I will talk also about this, but you can have application in the area of fiber optics, circuit and system user form automation, microprocessor, integrated architecture, serial and image processing that are applied in many different say cases like video games, medical equipment, or any type of other equipment. Artificial intelligence that now is very popular, for example, used in autonomous vehicle, but not only, or computer and communication networks used in data center that are again very, very important for today world. As I said before, wherever we can, we propose a hands-on approach. So learning by doing. We have laboratory, you have the possibility to do an internship that is 10 or 12 credits in the third year. And if you look at our program, second and third year, we have more than 20% teaching in the lab. Lab can be hardware lab. There is also a visit to our LED, Laboratorio Elettronico Didattica, or computer lab, where you do simulation, where you do other type of experiments. About mobility, we have also the mobility. I have to admit that mobility at PoliTo in general is more, let's say, offered at master level. So after you complete the bachelor, you enter in a master. But in ECE, being an international program, let's say like this, we have two programs also offered at bachelor. One is a double degree, so more intense program that lasts 1 year. You spend 1 year in China, in Tongji University. And then you come back and you take two titles, the PoliTo titles, the PoliTo degree, and the Tongji University degree. The second program is just, let me say, just 1 semester in US, in the Southeastern Conference. So it's a group of universities that you can select in the south of USA. I'm running a little late, so I will just go quickly over these two slides that are the professional profiles. So what you can do after you graduate in ECE, that is a bachelor. I want to go fast, not just because I have not so much time. I want to leave some time for your questions, but also because almost 99% of our students complete their study with a master. So they are not stopping after a bachelor, where you can become a telecommunication system manager, a digital signal processing system designer, or a junior ICT designer, or a junior engineer expert in assistant and mentor. Typically, our students complete a master in PoliTo, and I would say, unfortunately, also abroad, but I'm happy also for that, because it's a demonstration that our students, I have alumni that completed, that continued in a master in very high reputation university, both in Europe and also in US. So they are ready to enter in any program that they want. If you decide to complete your study at PoliTo, let's say the natural continuation is a master in communication engineering, that is, as the name says, covering technologies in the communication area. And then we have a second master in ICT for Smart Society, that is again in the area of communication, but is more about application. Application to smart society. What does it mean? Smart building, smart health, smart grid, smart energy. So everywhere ICT has an application, you need an expert in communication to manage, to design, and to handle it. Or you can stay in the electronic field. That is the second core of EC. Or you can also move to other, let's say, master program, computer engineering, mechatronics, that are also right here. In that case, maybe you have some, let's say, knowledge to be, further knowledge to be covered in the master. Even if EC is a very wide spectrum program, so it covers computer programming, it covers electronics, it covers communication. So to summarize, what are the EC strengths? It's an interdisciplinary program that opens you to many opportunities for your master programs. It's taught in English. You will be ready for a job in ICT where everything is in English, starting from datasheet, documents, and every company use English as a language in the company. It has an hands-on approach. So wherever we can, we ask students to learn by doing, lab, experience, computer lab. It has a small class of students. We have 110 seats per year, so it's not a very large course. And these allow you students a strong and effective interaction with professors. It is a good thing, so you can easily interact. So this concludes my presentation. There are my reference. You can stop at the booth, or you can ask now if you have questions. Don't be shy, ask.
What are the main differences between EC and Ingegneria Elettronica?
Okay.
Thank you.
Electronic here is just part of the program. For example, the whole communication area is completely missing in electronics. In electronics, they do something about signal, but for example, digital permission, communication network are not covered there. And also, as I said, using 3 ICTS, there are one in the second and one in the third year, you can even further, let's say, extend your knowledge about communication. That is the big difference. But you still have quite a lot of electronics. So you can, let's say, stay in this interdisciplinary program, take advantage of this interdisciplinary program, especially if you are not, let's say, so sure what you want to do after the bachelor, because these open you more, let's say, the spectrum of knowledge that you learn. You're welcome. Other questions? So if you have no other question, I will stop it here. If you have a private question, you can come now, or you can come to our booth that is just behind the door on the first floor. So, and thank you for your participation.